The model of an atom. In 1911, Rutherford beams alpha particle through a thin piece of gold foil. What you can see is that he beams alpha particle through a thin gold foil, and when he has the detector and move it around, he could plot the detector reading versus the angle, and this is the graph that he obtains. In the graph that he obtains, he concluded that main bulk of the alpha particle passes through undeviated. So one of the conclusions from the experiment is that the main bulk of the atom is mostly empty because the alpha particle could just pass through undeviated. The second part is that some of the alpha particle were in fact deflected, and that means there must be clearly a region which packs positive charge, but in a very small space. And that is when the concept of your nucleus come about. So understanding the concept of the nucleus, which comprises protons and neutrons, we're now able to explain why the alpha particle deflected, because alpha particle, like the nucleus, are both positively charged. And from the Rutherford experiment, we can now conclude that the atom, which comprises proton, neutrons, and electron, has its protons and neutrons packed in a small, dense region called the nucleus, while the main bulk of the space of an atom is occupied by an electron, which is primarily empty, as electrons behave both like a particle as well as a wave. And electrons, as we know, are negatively charged and have negligible mass. So to represent the proton, neutrons, and electrons, we have X, which is the chemical symbol of the element, and the number A represents the mass number, which is the number of proton and neutrons, or sometimes also called the neutron number, while Z represents the atomic number, which is the number of protons in the nucleus. In the case of a carbon atom, so for example, in this atom, we know that it is a carbon atom which has a mass number of 12 and a proton number of 6. Since the number of protons is 6, then from the mass number, we will know that the number of proton plus neutron must be 12. So therefore, the number of neutron in this case has to be 6. We use the term nuclei to describe an atom with a specific number of proton and neutrons. And these are the various examples of a nuclei. With the introduction of atom completed, we'll now get on to nuclear binding energy. In nuclear binding energy, we use the unified atomic mass constant to determine the mass of a nuclei. For example, if we have a carbon-12 atom, where the mass number of the carbon atom is 12, then we will know that the mass of a carbon-12 atom will be 12U, where U is equivalent to this value, and that data is present in the data booklet. And in the calculations of nuclear binding energy, we will need Einstein's energy mass equation, where E is equal to mc squared. The equation states that the energy of a body changes by E when its mass changes by an amount m, as in the equation. Meaning to say, if your mass decreases by m, then the energy equivalent to mass will be E equal to mc squared, and that energy will be released. Conversely, in the nuclear reaction, if a nuclei gain in mass, then the energy absorbed will be E equal to mc squared. It is quite common in the calculations of nuclear binding energy to be expressed in MeV, as 1 MeV is equivalent to the charge of 10 to the power of 6 electrons multiplied by 1 volt. So the charge of 10 to the power of 6 electrons is 10 to the power of 6 multiplied by 1.6 times 10 to the power minus 19 and coulomb. So that amount of charge multiplied by 1 volt will be equivalent to this number that's indicated here. And the energy equivalent to 1 unified atomic mass constant will be as calculated here, which can be equivalent to 931.5 MeV. Let's now define nuclear binding energy. Nuclear binding energy of a nucleus is energy must be supplied to separate a nucleus apart into its individual particles, specifically the nucleons, which are protons or neutrons. And we have to use the word separate and do not use the word breakup. Let's now take a look at the example as to how we can calculate the nuclear binding energy of carbon-12. So that is carbon-12. So before the 6 protons and neutrons are binded, this was the mass. After the 6 neutrons and 6 protons binded to form carbon-12, this is actually the mass. In this reaction, there is a decrease in mass. And hence, because of the decrease in mass, the binding energy using the formula E equal to mc squared will give us a value of this, or 89 MeV. Alternatively, there's another way to explain it. If we have a carbon-12 nuclide and we intend to separate it to 6p and 6 neutrons, we can see that the mass of the 6p and 6 neutron is larger. So in order for carbon-12, which has a lower mass, to produce 6 proton and 6 neutron, where the total mass increases, energy now needs to be provided in order to convert them to mass and to account for the mass increase. Hence, nuclear binding energy is the energy that's taken in to create mass. Hence, nuclear binding energy can be conceived as energy taken in to separate the nucleons and to create mass. Let's now take a look at nuclear binding energy per nucleon. How could that be calculated? So for example, in the case of iron 56, this is the nuclear binding energy. And we can divide the nuclear binding energy by the mass number 56. We will now get the binding energy per nucleon. We can do likewise for carbon-12, and we end up with this value. And if we were to plot the graph of the nuclear binding energy per nucleon versus the nucleon number, this is the graph that you got. It is clear that from the graph, iron has the maximum nuclear binding energy per nucleon, which means that iron 56 is the most stable nuclide as compared to other nuclides. Let's now take a look at nuclear fusion and then nuclear fission to understand how they can be used as nuclear power. In the process of nuclear fusion, 2 lighter nuclei combine to form a heavier nuclei. And the process is accompanied by energy increase. So example of a possible reactions is to take hydrogen nuclei to combine to form helium nuclei. In the process, energy is released. And using the nuclear binding energy per nucleon, we are able to explain fusion as lighter nuclei now combine to form more stable nuclei with higher binding energy per nucleon. And in doing so, energy will be released. In the case of nuclear fission, heavier nuclei is broken up to smaller nuclei. In the process itself, energy is released. In the nuclear fission, neutron, which is used to trigger the nuclear fission, will also produce more neutrons to cascade the chain reaction. And again, if you look at the nuclear binding energy per nucleon, heavier nuclei, like uranium, which is here, could undertake nuclear fission to produce lighter nuclei with higher binding energy. And in the process, they will have a lower mass and heat and energy will be released. So in both instances of nuclear fusion and nuclear fission, the energy released could manifest itself as heat energy, as kinetic energy of the daughter nuclei, or as electromagnetic radiation. So let us take a look at some examples. In the next example that we have both the nuclei combined to form your helium nuclei and your neutron. The 2 ways that now we can calculate that. One approach is via the use of E equal to mc squared. So we can sum up the mass of the daughter nuclei minus by the mass of the parent nuclei. In this case, the mass drop is this amount. So the mass drop will account for the energy release using the formula E equal to mc squared. And using the formula E equal to mc squared, we will arrive at the energy release. Alternative is to use the nuclear binding energy. We expect the nuclear binding energy of the daughter nuclei to be higher than the binding energy of your parent nuclei. And in this case, the nuclear binding energy of your neutron is 0. Hence, in the calculation of your nuclear binding energy, we can take the nuclear binding energy per nucleon of your helium, multiply by 3, because helium has 3 nucleons, and we can take the binding energy of your hydrogen, multiply by 2, because in this case, the mass number of your hydrogen is 2. And since there are 2 hydrogen nuclei, we have to add another 1. And finally, the difference between the nuclear binding energy is the energy that's released. And you can see in both methods, we both end up with the same answer, which is 3.26 MeV, amount of energy that's released as a result of the nuclear fusion.